Okay, good morning, and thanks to the organizers for inviting me to this meeting and to be able to participate in it. I will talk about broken paradigms, which is, I think, a good topic when there are lots of new graduate students and postdocs in the audience, because you obviously don't want to work on stuff that is well established. So I want to tell you about broken paradigms, which we have been hearing from all the previous speakers. So I'll continue in that vein, but I'm going to peel away a few more layers of complexity. So go away from cuprate superconductors, which are very complex. So of course you will break paradigms. But what if you have, oh, I didn't mean to spit it off here. What if you have just S-wave superconductors, where we know BCS should work? And yet I will tell you that even in this situation, there are paradigms to be broken. So I will tell you about band insulator to superconductor transitions, disorder-driven superconductor insulator transitions, and magnetic field-driven SIT, all within the context of S-wave superconductors, and show you how the BCS paradigm breaks down. But before going on, I want to address my missing picture in this racing women toward the high TC superconductors. And I think Erman left me out on purpose, because I think I'm racing toward the insulator. So my basic message is, pay attention to the insulator from which the superconductor is going to be born. And the reason is that that itself harbors some of the insights about the emerging superconducting phase. Okay, I won't go into that. Okay, so quickly, some of the systems to keep in mind. This is a classic picture for bismuth, which is grown with increasing thickness, or you can think of the thickness is increasing in this direction. And you can also think of it as starting with a superconducting film and increasing the disorder and driving it into an insulator. Or there are even high TC systems that we have seen show superconductor to insulator transitions upon hole and electron doping. And yesterday we had the twistronic session, and at each of the integer fillings, not just the ones shown here, at each of the integer fillings there are band insulators and other things that were just called insulators. Those are the ones to pay attention to, the structure of those. But in all of them there are nearby insulating and superconducting phases. So basically you can tune the SIT by disorder, magnetic field, doping, gating, pressure, a number of knobs, and the phenomenology from all of that is what I will get into. Now, connecting with Seamus's talk, there he walks in, Seamus. Almost. Okay, so he touched on these local spectroscopies, and I'm going to get into that in quite some detail from the theory side. One particle density of states, Josephson Spectroscopy, compressibility, also locally measured by changing the local chemical potential and measuring the change in the density, and diamagnetic susceptibility, which people haven't talked about, but this is yet another probe of the local diamagnetic currents in a superconductor. And we have applied a number of theoretical techniques, because at some level you don't want to take a system, put all the complexity in it, say we have done the best theory possible and this is what comes out. That's like doing a numerical experiment, which is not going to give you any more insight than the complexity of the original experiment. So it's useful to take simple models, apply a sequence of theoretical methods that give insights. They may not be exact, but each one will give us some level of insight. So I will talk about mean field theory and then add fluctuations to that using quantum Monte Carlo, make ever increasing coarse-grained models to a quantum XY model, and I will try to push the envelope on this and get spectral functions out of quantum Monte Carlo information. So if some of you here do this kind of theory, getting spectral information out of imaginary time data in Monte Carlo is extremely difficult, but we have been able to get spectra. So I will show you all of that. Okay. So this is kind of the summary of the 3 parts to my talk, and we'll see how far I get there. But it will be on the insulator to superconductor transition, and sometimes I say superconductor to insulator. It just depends on which side you understand and which one you are trying to get toward. And the main message of my talk is look toward the insulator, and the seeds of pairing are found right in there. And they become coherent as you go toward the superconductor. So very quickly about the BCS paradigm, which you all know, but you start out with a large Fermi surface, and when you turn on some coupling, some attraction, it opens a gap. On the Fermi surface, the gap scale is much, much smaller than EF. That's when your Cooper pairs are large and the BCS paradigm works, which basically is a statement that everything is controlled by this, by the gap or the order parameter in the amplitude of the order parameter. Now, how can the BCS paradigm break down? If the glue, the coupling with your source that is providing the pairing becomes too strong, and the Fermi surface is perturbed not just on a small scale around EF. That's one way when the glue becomes very strong, the BCS paradigm can break down. Another way is if you go away from the adiabatic limit, where essentially the pairing glue, the time scale for that, is much slower than the time scale for the electrons. Now, another feature that we don't pay attention to when we are talking about the BCS paradigm is the full nature of the order parameter. The order parameter in general is complex. The amplitude of that is what is playing a role in the BCS theory, but it also has the phase degree of freedom, which are basically these gapless Goldstone modes that that are soft and produce the fluctuations going around this Mexican hat potential. So in a quick summary here, we use these 3 features sort of analogously in the BCS theory: the single particle gap, the order parameter, and the pairing amplitude. And I want you to pay attention to that, because when I add disorder, you will see that they are not going to be proportional to each other or related to each other. They will all have very different behavior. So this is shown here. Okay, so that's the first part here. The second property, which is sensitive to the phase of the order parameter, is shown here. So in the ground state, in the ground state at 0 temperature, your phases are aligned. If you now twist the phases by applying some boundary condition, then that forces these phases to adjust to this twist continuously, and that raises the energy. And that the increase in energy, so the second derivative of the free energy with respect to this twist angle, is a very important defining property of the superconductor or the superfluid that I call the superfluid stiffness. And I kind of analogously call it the superfluid density. But this is different from the way Seamus used the word. So this is really a stiffness of the complex part of the superconducting order parameter. So you can get the single particle gap from the density of states by looking at di dV. And you can get the superfluid stiffness either by doing a mutual inductance experiment and measuring the inductance, or you can get it from the absorption, the real part of sigma of omega versus omega. You don't get any absorption until you hit twice the single particle gap. And there's a sum rule which controls this, this absorption. So the total integrated weight is a fixed number. And this is the absorption at finite frequencies. But in addition, there is an accelerating part of the condensate which appears at 0 frequency, which is this added weight. So so in the experiment, you really measure this part of the absorption. You know the right-hand side, and from the difference, you can get the superfluid stiffness. So this is the way you can get the two important properties of the superconductor, the gap and the stiffness. And in general, the gaps are very small, on the order of milli-eV. The superfluid stiffness is a very large energy scale. For aluminum, for example, it's on the order of EF. But as you increase the temperature, both scales vanish simultaneously at Tc. And that's the transition. Okay, now going beyond that, let's say you start increasing the glue, which is this attraction, let's say, that's G. What happens is the pairing scale will start to go up and increase with the glue. So the greater the attraction, the harder it is to break pairs. However, the superfluid stiffness is either constant or decreases with G, and at some point these two energy scales cross. And that part is important because what it says is that Tc, the transition temperature, is governed by the lower of these two energy scales. So at small attraction, it's really the pairing which is describing your transition, and that's the BCS paradigm. But at large coupling, since now ρS has become the smaller scale, that governs the transition. So essentially the superconducting transition is being governed by not a closing of the gap, but with the gap is still finite. You can see in this region here, the gap is still large, but it is being destroyed by the phase fluctuations, which are ultimately becoming extremely soft at the transition. And that's why ρS is vanishing. So this is now very well understood. I want to push it even further now toward all the way to an insulator. So let's say we have some way of tuning. As I said, there were multiple ways of tuning the transition. And I've just shown you a sketch here. This is the superconductor with a finite Tc. You go through a sequence of curves. Then there's a separatrix here with a resistance scale, which is the quantum of resistance, h over 2e squared, and then the insulator. So I can plot this in a different way as a function of G. Here is Tc coming down, vanishing at the critical point, and supposedly another energy scale on the insulating side, which also goes soft. So what are some of the big questions in this field? What is the type of insulator on this side? That is something we would like to understand. What is the nature of the superconductor, especially close to the quantum critical point? What is this energy scale? Here we know it is Tc, which is kind of the minimum of either delta or ρS, as I described. But what is really the scale on the insulating side that is going soft? Is the quantum critical point fermionic, described by broken pairs, or is it bosonic? And is there a metallic Bose metal phase in the middle? That's still something I won't go into here, but that is an interesting question for the community. Okay, so let's enter part one. I'm going to take a really simple problem of a band insulator on which we will add attraction and see the fate of that insulator toward a superconductor. This work was done with these collaborators. Mohit Randeria is in the audience, and this paper was published a couple years back. So the question I want to understand is, can an insulator become a superconductor? And you keep in mind our picture of the Fermi surface, which became unstable as we turned on attraction. we go all the way to a system that has no Fermi surface. And the question is, how is a superconductor born out of this? And how does even a BCS superconductor get born in such a scenario? Okay, so always good to have a Hamiltonian. We were discussing this at lunch. So here it is. Theorists should put up their Hamiltonians. So I've picked a particular Hamiltonian, and I'll tell you why. It's an attractive Hubbard model, attraction because we want to study superconductivity. And I've picked a bilayer because we want a band insulator. So either you can take a single layer with 2 atoms per unit cell or 2 orbitals per unit cell. Here I've just taken 2 layers. And the reason I've picked a triangle rather than a square is just because I want to avoid any other competing orders like charge density wave and so on. You can't do that in an experiment, you get what you get, but we can control this in our model. So here is a hopping on a layer controlled by the energy scale T. There's a hopping between layers on these rungs controlled by T perp, and U is the attraction. And I'm going to work at a filling of 1 electron per site. And the reason for that is I want to stay in a band insulator. So here is my phase space that I would like to fill up. I want to get all the phases here. This is the attraction in units of T perp. T perp will set my energy scale. And this is the hopping in units of T perp, hopping within the layer. Okay, so here's the band structure. This is at a small value of hopping within the layer. So in a way, little t controls the bandwidth of these bands, and T perp controls the separation between the 2 bands. So at small values of T, I basically have a band insulator. And at a greater than a certain critical value, you can see now I get states within around the chemical potential, and you go from you go into a metal with these pockets. Now what I will show you is based on, again I don't want to go into too much detail here, just to give you the overview, that we do very different kinds of calculations in different regimes of this parameter space. Clearly you can see this is ideal for testing many different approximations. So when U is small, then we can do diagrams and mean field theory. At 0 hopping, we can essentially analyze the atomic limit. At strong coupling, we can map the problem to bosons and look around that limit. And really in the middle, when all the energy scales are of order 1, then you have to use quantum Monte Carlo. And the result of that is a phase diagram like this. You have 4 phases. This Fi is the Fermi band insulator. So think of a cut going like this. At small hopping, you have a Fermi band insulator. And what this picture says is that you cannot directly go from a Fermi insulator to a BCS superconductor. You necessarily will go through 2 intervening bosonic phases. The slivers may be very tiny, but there will be a regime where at some finite attraction, the Fermi insulator will become a Bose insulator, and I'll tell you precisely how we define that. And then there will be a transition to a BEC, and then a further crossover into a BCS superconductor. But that is going to be the fate of this Fermi band insulator at, let's say, a fixed value of the attraction as we turn on the hopping within the layer. Okay, and on the other hand, if you sit at a particular value of the hopping and just increase the attraction, then you need not, depending on where you are, you need not go through all the phases. The Fermi insulator could just become a Bose insulator and it could remain insulating. So the behavior is very different depending on how you tune through this. Okay, so what exactly are these phases? I'm going to show you that through a couple of sketches and then some actual results. So here is the Fermi insulator with a valence band and a conduction band and a gap. This is the single particle gap. So this is at zero attraction, so as you increase the hopping, the bands are going to get wider. At some point they will overlap and the single particle gap will close and make a transition into a metal. Now if there is a finite attraction, then what you find is that there is you can make a pair of holes within the valence band and a pair of electrons in the conduction band, and there is a two-particle gap that still can be a two-particle gap that is finite and within this region here. So what you're seeing is at zero hopping, the energy to create two particles would have been twice the energy to create a single particle, right? Because you have to take two holes and put them into the conduction band. But if there is some attraction, the two-particle gap can start to become lower at some value of the hopping and dip down below the one-particle gap. When that happens, the system makes a transition from a Fermi insulator, where the single particle gap is lower than the two-particle gap, to a bosonic insulator, where it becomes cheaper to make a two-particle excitation compared to a one-particle excitation. So this is the precursor to the superconductor. So now at some point, this two-particle gap will go to zero, and that's where the insulator will enter a superconductor. So there's no way that if there is a superconducting state lurking nearby, there is no way to go from just a single particle gap state directly to the superconductor. You will go through a bosonic state intervening. Okay, now in the superconductor side, again you see that so what we find is that the single particle gap in fact remains finite throughout this insulator to superconducting transition. On the Fermi insulating side, the single particle gap is just that one particle gap I showed you. It enters a BEC regime where the single particle gap is this geometric mean of the one particle gap in the spectrum and delta square. Delta square is now the gap in the superconductor. And then when you at a point where this is the one particle gap that I had shown earlier that was closing at some value of the hopping, giving you a superconductor to metal transition at zero attraction. When that happens, this single particle gap goes to zero, and then of course ESP, the single particle gap, just becomes delta. So that's what would happen in a BCS superconductor. So now this kind of summarizes all the gaps. And the important things to take away from here are the bosonic phases near the transition. There is a bosonic insulator as well as a bosonic superconductor that I'm calling a BEC, and here it is characterized by having a gap scale which is a geometric mean of these two. The superfluid stiffness, which I'm not showing here, is again also something that will be zero all through the insulator, and it will start picking up in the superconductor, and it will start increasing and go above the delta scale in the BCS superconducting side. So that's the summary of the gaps that I just sketched, but we have two very specific, the BCS-BEC crossover is really a crossover scale, so you can look at it with different quantities. If you go look at it through the spectrum, we have two very definite predictions that if you look at the ARPES and look at where the ARPES has a band bending, and from that pick out the minimum gap locus, it has a very different behavior on the BCS and BEC sides. So let me just point that out here. This is what you are familiar with. This is the energy as a function of momentum or as a function of the bare energy. And you can see it is just linear far away from the chemical potential, and then there is this bending right around the chemical potential. So if you look at this minimum gap in momentum space and map out that contour, it's going to be a contour which has a size of the Fermi energy, and it's a closed contour. In the BEC side, your chemical potential has become negative, so the minimum gap is really happening at k equal to 0 and becomes a point. So the shrinking of the minimum gap contour to a point is another very specific signature of the BCS to BEC crossover. In tunneling also, this density of states has a very different behavior. You can see that if you have this minimum gap locus which is happening at mu, it automatically gives you like a Van Hove singularity with the square root singularity in the tunneling density of states. That's what we are familiar with in the BCS regime. In the BEC regime, because everything has shifted to negative chemical potentials, this the change in the dispersion gives you now a step in the tunneling density of states. So these are some predictions that would be nice to see corroborated in experiments. Here is some, I made these sketches just because sometimes these are easy to take in, but here are some quantum Monte Carlo data for the same model that I talked about, where we calculate the Green's function in imaginary time at each point in k space. And from the decay in tau, we can extract the energy as a function of momentum. And you can plot that, E as a function of k. We can do it in both regimes, the BCS and the BEC, and you see this very different dispersion relation. Here you see this band bending at a finite value of k. When you map it out, it is this closed contour. Because it's a triangular lattice, it has this shape. And in the BEC side, the band bending happens just at k equal to 0. I mean, it's not at fine. This whole picture has moved to k equal to 0, and you get that minimum gap locus at the gamma point. Okay, so very recently, there are some very beautiful experiments by Amit Kanigal's group, and Mohit is a co-author on that. It's on iron selenide. In most materials, this has been the problem of how to tune toward a BEC regime. And you can't tune the interactions very much. They are whatever are given in the material. In cold atom experiments, it's possible to tune the attraction using Feshbach resonance. In materials, on the other hand, what is important is to tune this ratio, delta over EF. And what was done in these experiments was to use iron concentration to tune the Fermi energy. So in that way, rather than making delta large, they were able to make EF small and thereby increase delta over EF from 0.16 to 0.5. And you can see that, in fact, this is the spectra at the two levels. And here is a fit which shows very clearly that at when delta over EF is small, 0.16, the band bending happens at some finite KF. And here, when you go toward the BEC regime, the minimum of the gap is at the gamma point. Okay, so that's part one, and here's a summary. So anytime you see a superconductor to insulator transition, my message is look close to the transition. Neither the insulator nor the superconductor is going to be your average type. The insulator will already have signatures of pairing. In that, the lowest excitation should have charge 2e, should be bosonic. And even on the BEC side, if you can do ARPES or tunneling, you should see either a minimum gap locus at the gamma point or a step-like density of states. Okay, part two. Actually, this part is what we had done first. You can see it was like 1998, and then there was a bit of a pseudo gap of about 10 years here, and that was still disorder-driven superconductor to insulator transition. And then we really started thinking, can we make the model even simpler? And I reversed the story today by telling you about the band insulator first. But let me come to the part where we now just take one layer. And it's a superconductor with, let's say, some model as some attractive model, Hubbard model. And we start to add disorder. And again, we will drive a superconductor to insulator transition, and we can ask the same questions. What kind of superconductor, what kind of insulator, what is the transition? So we are talking about, this talk is all about broken paradigms. So here's another, I talked about how the BCS paradigm breaks down. Now we bring in disorder. So again, we have a very standard paradigm for disordered systems with no interactions, and that's Anderson localization. And now we'll bring these two together, and what you will see is both paradigms will break down. So there'll be no regime, and let me show that. And so there'll be no regime where the Anderson localized, even at weak disorder, you will see that the Anderson localization kind of behavior in the presence of attraction will break down. Okay, so stepping in, let's say when we have weak disorder, this was discussed back in the 60s by Anderson, Abrikosov, and Gorkov, often even known as the Anderson theorem. So essentially the point is there's no effect on thermodynamics if KFL is much, much greater than 1. At moderate disorder, there was work by Finkelstein in the presence of Coulomb interactions that TC would get suppressed. But I want to really come towards strong disorder, near the transition where h over 2e square is that quantum of resistance. And ask what is the nature of this regime. So here's another sketch which summarizes the phase diagram. And then again, I'll give you the details of the calculations from which such a phase diagram is derived. Okay, so let's look at this, the two energy scales, the single particle gap and the superfluid density or the superfluid stiffness. Both vanish at Tc. This is a standard BCS superconductor with no disorder. And now I add this axis, which is disorder, and you should think of it as just random inhomogeneities on some very short length scale, atomic scale. And what you see is as this is cranked up, what I will show you is that the energy gap, the single particle gap, again, just like in the story I told you, will turn out to be finite. But what will go critical is the superfluid stiffness will vanish at some critical disorder, and beyond that the system will become insulating. So again, you will see a regime where rho s is bigger than the gap. This is kind of a BCS regime. Then a crossover to a regime where rho s becomes smaller than E gap, and that will be a BEC regime. The transition then takes you into an insulator, and again, there are going to be two scales in the insulator, the single particle gap and a two particle gap. And I will show you that the energy for pair excitations will go soft at the transition. So to answer that question at the beginning, what is the energy scale that is going soft from the insulating side? It is the energy to add pairs into the system. So that scale will go soft at the transition. So this regime here is a bosonic insulator. Okay, now how do these things come out? This is the theory behind it. Here is the model now. It's an attractive Hubbard model. Now we revert back to a square lattice because we don't have competing orders when I have random potentials. The randomness is put in the chemical potential. And what is nice about this model is you can turn off the attraction and just study the localization physics, or you can turn off the random potential and then you have superconductivity, and all the BCS-BEC crossover is contained in the strength of U over T. So it's a really very nice model. Okay, let me go through this. Okay, there are different approaches here. The first one, which is called the pairing of exact eigenstates, you put all your randomness in the single particle states, and then you pair these states. That gives quite a lot of insight into some of the inhomogeneity that develops. You can go beyond that, still within mean field theory, do Bogoliubov-de Gennes mean field theory, where you allow your inhomogeneity in the delta potentials and the densities and you solve for that self-consistently at each site. And from that you can get the local pairing amplitude delta and the local density for a given random potential that you input into the system. So these methods are quite powerful, but they ignore any phase fluctuations. Remember I said the order parameter was complex. Those fluctuations are not included. So in the ground state, when you have a superconductor, the phases are all aligned. So we can include that in Monte Carlo. And what is important is you have two kinds of phase fluctuations. As a function of temperature, of course, the phases will fluctuate thermally, but even at zero temperature, you can have quantum fluctuations, and both of those are included in Monte Carlo. And furthermore, we would like to not just get the Green's function in imaginary time, but to compare with experiments to get these density of states and spectra as a function of omega. Okay. So this is what we find. The focus is going to be on getting the real space maps of the local pairing amplitude. I use my words now very carefully because all of these different scales, which were very similar in the BCS theory, start to become different. So this is the local pairing amplitude. And when there's no disorder, of course, it will be homogeneous, the same everywhere. When I crank up I put some random potential and I take some profile, I'll show you that the map of this delta of R starts to show this inhomogeneity. So there is some region in space where delta is large, separated from other regions where delta is zero. As the potential strength is cranked up, keeping the same random profile, you see them breaking up into these kinds of blobs. Where I should have colored this, delta is large here within the blob and zero outside. So there is this emergent granularity. And that's a concept I want to discuss in some detail. It also connects with what Seamus talked about. So these are now the real results from Bogoliubov-de Gennes calculations. And you see that I'm taking this phase diagram here, temperature disorder at low temperature, cutting across like this. The phase transition where superfluid density vanishes happens somewhere kind of close to this region, and you start to see the formation of these patches or puddles where the order parameter is large, black is large, white is zero. And what I want to stress is that the scale of this emergent of these patches. So the structural disorder is on kind of an atomic scale. So these are not electronically inhomogeneous. They are electronically basically homogeneous. But in the presence of even this homogeneous disorder, what is emergent are patches on the scale of the coherence length psi. You know, some kind of a disorder coherence length, C naught L square root. That defines this patch size. Now, you might ask, can this local pairing amplitude be measured? You might think, you know, the gap is essentially revealing what my order parameter is in the clean system. So just do a tunneling experiment on the patch and in the region outside that. And what I will show you is, you may have thought that if delta is zero, the gap should be zero. But what I'll show you is that the local pairing amplitude and the local gap in the spectrum are anti-correlated. So that's one very important result. So the spectra on the patch will show this nice coherence peak and a gap scale, but when you go into these white regions, the gap scales are larger and there are no coherence peaks. So here's the evidence for that. This is from actually beyond even Bogoliubov-de Gennes. This is including the fluctuations. This is the local pairing amplitude map at some value of the disorder where you have these patches. And this is the local gap. So at each point I have taken that spectrum and extracted the gap, and I have inverted the scales. So here dark was large pairing amplitude, here dark means a small gap. So you can see that on the patch, the gaps are smaller. In the white regions, where there was no pairing, the gaps are larger. So this anti-correlation here. And this is the actual spectrum in these different regions, and that's the result. And the reason for this is actually quite interesting. When you have a random potential, the states near the chemical potential are the ones that will be used to make these superconducting patches. So they obviously end up having the superconducting gap. The states that are further from the chemical potential are the ones that contribute to these white regions, so they have sort of the one particle gap because they are away from the chemical potential.
Sorry, may I ask a question? If you would have enough size to consider the Q dependence, would that all happen at Q equals 0, or?
So right now I'm taking one realization of disorder. So to get Q, I would have to average over disorder. Okay? And then you will lose this kind of a correlator. So I'm taking one realization, one sample, and I'm doing it there. Okay, so now you can see that what has happened is the emergent granularity has taken us outside the BCS paradigm because the amplitude has become inhomogeneous, but now the phase degree of freedom that we might have ignored up to now starts to become important. Each of these patches has a phase. On the superconducting side, they are well aligned through the Josephson coupling between these patches, but if due to increasing disorder or whatever your tuning parameters, the Josephson coupling is weakened, then you go into a regime where the quantum fluctuations are able to destroy the coherence and give you an insulator. So that's really the picture of the superconductor-insulator transition. So here are some more results showing now how we calculate different things. For example, the superfluid stiffness is obtained by a current-current correlator, and what you have is sort of like your helium experiment, where if you want to measure the superfluidity, you try to take your liquid in a pipe and push on it longitudinally, and that gives you the total density. And if you now try to shear it, only the normal part contributes. So that's a different limit of this current correlator. From the difference, rho minus rho n, you can extract the superfluid density. And that's what is shown here as a function of disorder. The single particle gap remains finite. So the amplitude is not going to 0. But the superfluid stiffness, precisely because of these patches which are getting uncorrelated due to quantum fluctuations, that is decreasing and vanishing at some critical point. Okay, few more. This is like ramping up now our color plotting abilities. So these are all theoretical results showing now a cut like this at low temperatures. This is the single particle density of states. And you see the hard gap remains, so the hard gap continues through the transition. The transition is indicated by this white line here, which is where the superfluid density vanishes. So this is the superconductor, that's the insulator. The hard gap doesn't know about it, but the coherence peaks do vanish around the critical point, but really this sharp transition is obtained by seeing where the superfluid density vanishes. Now we can also take a cut like this and fix the disorder on the superconducting side, but increase the temperature. And now you see that this is again this single particle dIdV as a function of omega. You see the hard gap starts to fill up. Do I have a, no. The hard gap starts to fill up, and again this is where rho s vanishes at the transition. This is the costless, taugless transition with a jump. This is the finite temperature transition. But you see even beyond that, a pseudo gap persists at finite temperatures. So the importance of some of these results in view of the cuprate story is it's able, even though the actual microscopics is very different, that's a repulsive problem, and magnetism is important. Here we have, without worrying about the origin of the superconductivity, we have some attraction, but it is important to see the phenomenology that emerges. And here we see that in a nominally BCS superconductor, by adding disorder, we can get this kind of a pseudogap. In this case, it is entirely due to pairing. So pseudogaps can have many origins, could be what we heard earlier, but here it is entirely due to pairing. Or in other words, these patches remain, and it's the phase fluctuations that become soft at Tc. So even above, in the normal state, you still have pairing on these patches. This is some scanning tunneling spectroscopy data on this sample here is indium oxide, and what they have done is sitting on one of these superconducting blobs, they have taken the data at different temperatures. The dotted line is Tc. This is the transition temperature. Below that you see these sharp coherence peaks, but even above that, the gap, the pseudo gap is persisting at finite temperatures. So that's a very nice corroboration of our results. So far, so this is what I showed you from the theory. They have also mapped out, they cannot measure the local pairing amplitude, but they have looked at where the coherence peaks are sharp and mapped out that the sharp coherence peaks, and they see these kinds of patches forming at a particular sample. Okay, next we want to go toward Josephson spectroscopy, where we try to tunnel two particles into the system, as we heard about, and that would be essentially a delta-delta correlator at two different sites and at two different times. So this is constructing a Green's function of pairs. So if I look at, so I'll show you the local spectroscopy where these two sites are the same. Okay, so this is just summarizing that. So here is a particular value of the disorder, enough to give me these local pairing amplitude patches. This is the one particle spectrum we talked about that was anti-correlated. I have made the same contours and taken from the local pairing amplitude here. So you see that within the contours, while you had a large pairing amplitude, you have a low density of states that we talked about, that anti-correlation. But if you look at the two particle spectrum, that is large on the precisely these patches where the local pairing amplitude was large. So that would be an experiment that is, I would say, really would be extremely useful to combine the single particle and the two particle and close this loop on that. So while the local pairing amplitude cannot be measured, it has positive correlation with F and negative correlation with the single particle one, producing anti-correlation between these two maps. Okay, this is now back to our quantum Monte Carlo results, showing now the energy scale. I want to come back to that. What is the energy scale that goes soft? This is the energy scale can be obtained now from P of omega. So, Erman, your question, if you now average over the whole system and just do a tunneling spectroscopy with a superconducting tip, let's say, then you would see on the superconducting side at zero energy or zero voltage, you can insert Cooper pairs. But as you enter the insulator, that peak will split, and the energy scale of that splitting is something you can calculate or measure. And what we find in our case, we calculate this, that energy scale to add a pair into the system goes soft precisely at the quantum critical point. So this then summarizes basically the disorder-driven SIT, the single particle scale is always finite as a function of disorder. On the superconducting side, Tc is becoming small, and this Tc itself is interesting in terms of whether it is determined by amplitude or phase. Close to the transition, it's determined by the phase. Far away here, it's determined by the amplitude. And then entering the insulator, the two-particle gap is of course 0 everywhere in the superconductor, but it starts increasing with some exponents here toward the insulator. Okay, so that's the situation of part 2. I'm not going to go into this too much, but as we understand one level of the theory on some level, we can start coarse graining. And now that we know we have these patches, and really the behavior near the transition is governed by phase fluctuations, we can start to build models of Josephson arrays, a quantum Josephson array model, where the patches become the sites of two-dimensional network, and these phases are coupled through some Josephson energy, Ej, and what competes with that are the number fluctuations. So there's a charging energy on each of these patches or grains, which has a strength EC, and because these two operators don't commute, that's what builds in the quantum fluctuations that drives this transition. So this model allows us to now look at much larger sizes because we have coarse-grained the model. And in particular, what it allows us to do is to look at these diamagnetic currents on a local scale. So this brings us to our recent collaboration with the Kaliski group, where they can use a scanning squid to measure now not on nanometer scales but on micron scales. And they can use this squid to pick up the susceptibility. So in a superconductor, the susceptibility ideally would be -1. Now the diamagnetism, because of these patches, the diamagnetism is also patchy. Some regions that are more superconducting. So now I'm not talking about the superconductivity within a patch, but the connections between the patches drives supercurrents. And these supercurrents would give you diamagnetism on the scale of microns, and they can do this sort of scan squid measurement and map out these the distributions of the susceptibility. And what they find is, so these are 3 films. Again, it's being tuned by disorder. When they are far away, what is shown here is the resistance becomes, this is all the 3 plots are scaled with T over Tc. So that means the thermal fluctuations have been accounted for. So this is T over Tc of 1, and what you see is the susceptibility, diamagnetic susceptibility, the sign has been reversed, is large in the superconductor and vanishes at the transition. As you come toward the quantum phase transition, you see that the susceptibility distributions are becoming extremely broad. And that's because of this growing inhomogeneity. Okay, so ending the second part then, the key points are listed here. There is emergent granularity, spatial inhomogeneity in the local pairing amplitude, and as I said, the 1-particle gap persists, the 2-particle gap is going soft at the transition, and the stiffness is controlling the behavior on the superconducting side. Okay, so how much time do I have?
4 minutes.
Okay.
Till 10 minutes.
Okay. So let me come to the last part, which is now we want to now look at the magnetic field-driven transition. So let me just say very quickly in words that if there is no disorder, we have the standard picture of applying a magnetic field, getting vortices. These vortices form a triangular lattice. The core of the vortex is metallic. And at some point, as you increase the magnetic field, the vortex cores overlap, and you get a metallic state. So that's the superconductor to normal transition that would happen in a BCS superconductor with Abrikosov vortices. What happens now if I take this disordered system and add a magnetic field to that? Now here there is a very important puzzle in the field that has remained for several decades now, or at least over a decade, and that's the following. So here's the resistance versus temperature. This is magnetic field now. You see a superconductor at low magnetic fields. Then there are a sequence of scans where the transition is moving down, and then it becomes an insulator driven by magnetic field. I'm going to take that kind of data. I haven't shown this. This is a sketch. But I'm going to take now, this is real data from the Shahar group, resistance as a function of field now for various temperatures. And the key thing is to look at this critical point here where you see the lower the temperature you go to, the higher the resistance is beyond the transition. And if you look at that, so that B critical is somewhere right here. This is a much expanded scale. The B critical is somewhere here, and you see beyond that a very, very large positive magnetoresistance. The origin of that, of this behavior has not been understood until what I'm going to tell you. I believe we have some understanding of this very strange behavior. Also, the peak is very asymmetric, it rises sharply near the critical point, and the higher the disorder, the more the peak grows. Okay, so in the last some minutes that I have, let me just sketch out the phase diagram we get, again using the different methods I talked about. So here is disorder, which we understand now, and now I add another axis, magnetic field. And what we find is that the critical field, where rho s vanishes, the behavior of the critical field that separates the superconductor from the insulator has this very non-monotonic behavior. So at low disorder, what is happening is the vortices are going into these inhomogeneous patches. So they are like your Abrikosov vortices that enter a superconductor with cores where the order parameter is suppressed. These are what I call Abrikosov vortices. And as you increase the field, that's the metallic state. But on the other side, at large disorder, you get these Josephson vortices, where the core of the vortex is sitting between the patches. And so when you go up beyond some critical field where you lose superconductivity, you don't go into a metal, but you go into this bosonic insulator. At even higher fields, which is not shown here, the bosons will now start breaking apart into fermions, and you'll see another crossover into a Fermi insulator. But this is kind of the origin of that huge magnetoresistance where instead of going from a superconductor to a metal in a field, you go from a superconductor to a bosonic insulator and with a huge resistance in that phase. Okay, so I'm going to skip some, we have some spectroscopy of the cores and so on, and I know Erman's group is very interested in this core spectroscopy, but I'll skip that and maybe just show you, conclude with my talk on these broken paradigms with just the phase diagrams. And so here I want my takeaway messages to be the case where you had the band insulator to superconductor. This is the disorder one, and the third one was the magnetic field case. And in all of these cases, what I want to stress is that there is a regime where you have a BCS superconductor, an ordinary S-wave superconductor. And yet, by either putting it near the band insulator or by adding disorder or by adding magnetic field, you can push it way outside the BCS to BEC, but even more into interesting insulating states. Okay, thank you. Questions? Yes.
generically about the nature. In particular, in the calculations, I guess it's like point disorder, like atomic size, you said. But we, for example, the like domain disorder or orientational disorder, like polycrystalline-like, for example, is that actually disorder even if it's not points capitals?
Right. So you could put all of these different kinds of disorders in my language would be what I would call chemical potential disorder. And you could put it, I've put in generic, random disorder at every site. You could put in, like you could say, okay, there are some impurities, then put in some potential disorder there, or line defects and so on. Pretty much the same phenomenology will go through. What would be different is if you put in disorder, let's say in attraction, U, and if there are places where U becomes 0, like some places that you force to become metallic, then the phenomenology will be different. But any kind of generic disorder would work. Another point to bring up here is disorder in the hopping. Okay, the hopping has a certain sign. So if I put in disorder in that, it's like changing the Josephson coupling between the grains. If you change the sign of the Josephson coupling and make it negative, then that's another way of putting in frustration. So then the story can be different. Because once you put in frustration, now in your ground state, you can start getting gauge fluxes around plaquettes. So these are some extensions. And I bring them up because really it's a very rich problem. And since there are students here, there are all of these directions you can push into.
One more student, or two more students, and then a mother. Yes, back here.
Yes, could these paradigms be realizable in other kinds of superconductors?
You mean like say D-wave or? Yeah. So you would have to change some things fundamentally, like the very starting Hamiltonian. If you make it a positive U Hubbard model, then you would get, then you would get the TJ model out of that. And in that you could, and we have done this. We have looked at a repulsive Hubbard model or a TJ model and added disorder to that.
Okay.
And the results are different because obviously D wave you get a point node, so you get gapless states. But again, what is important is D wave superconductors are actually extremely sensitive to disorder. That's what we believe, or that's what can be shown for weakly coupled D wave superconductors. But these cuprates are not that. They have short coherence lengths, and you can show that the effect of disorder on that is much more robust. And yeah, I can give you some references.
Okay. Thank you.
There was a question? Yes.
Well, first of all, thank you for your talk. And I was interested in when you talk in the second part about the disorder-driven. There was some slide about titled "The Pseudogap Persists" about TC, and you commented something when you were talking about the transition about Clauselitz bullets, and well, as far as I know, that's something related with the topology, and I was wondering if you could extend a little bit more in the topology of the thing, if that makes any sense.
Yeah. So the point is that at 0 temperature, the transition, let's look at this one. So if it's a two-dimensional system, right, I've sort of suppressed some things here, but let's say it's a two-dimensional system, this transition at 0 temperature is in the universality class of 2 plus 1D XY model. So it is a continuous transition with exponents, z nu and 2/3 and so on. But if you go to take the same system and now add temperature, so that's the plot you are referring to, I'll come to that. This one, right? So here at finite temperature, it's a 2D system. The transition would be a costless-Thouless transition due to the unbinding of vortices. And in that case, the superfluid density has a jump. And that's what we calculate. So we don't see a jump because of the rounding in a finite size system, but you can make that linear 2 over pi Tc plot and get Tc from that. And that's how these white transitions were obtained, basically applying finite size effects on the costless-Howless transition.
Any other question from? Well, one more.
Oh, okay. So maybe you mentioned this, but the resistive transition in terms of temperature for this, disordered case, I guess that would look quite different since you still have like superconducting patches, but they lose coherence. So how would that look like?
Yeah, so we have done quantum Monte Carlo on that. I don't have that result here. So again, resistivity, it's the first measurement experimentalists do, but theoretically it's hard to calculate. But we do calculate that current correlator that I mentioned, but a different limit of that gives you resistance. So we can calculate, on something, so we are able to get the resistance versus temperature and get Tc, and then you can see the whole sequence of curves, just like the experimental curves. And the transition, in fact, I should include that, it's rather beautifully at the quantum of resistance. So we obtain it from the current correlator. Are you a theorist or an experimenter? Okay, good. So if you're not to say good for the explanation, that we look at the current correlator at tau equal to beta over 2, and that can be related to the resistance. Okay. Okay, now an experimentalist question.
Amalia.
So my question is related to the BCS-BC crossover, which it suggested to be present in some systems where the Fermi energy is close to the gap. But often the systems where it's suggested are multi-band systems when there are more bands with different Fermi energy. And I wonder, is this correct for us to call them the system in that regime or not, when you have multi-band systems?
Right. So you could take an experimentalist point of view that you will look at so you can look at the minimum gap, and so you're basically looking at the two measured quantities, the gap and the stiffness. The stiffness is an overall macroscopic quantity, but the gap depends on each band. So you could take sort of you could compare your rho s and with the minimum gap and see where that switches to give you an idea about the BCS-BEC crossover. You could also extend the whole thing, especially if there is information on each band. You could look at the band bending on each band. And then some bands could be in the BCS regime and some could be in the BEC regime. That's possible. It's very much like also Mott selective behavior in transition metal oxides. Some bands become Mott-like and some are itinerant.
Orbitally selective.
Pardon?
Orbitally selective.
Orbitally selective.
So you're saying that if the gap, and I related to other quantities, dominate the other quantities which are microscopic, then I could call that a pure BCS, the BC crossover system.
Yeah. But it brings in the richness. You could go through, like now, multiple crossovers, right? There may just be one phase transition, but there could be multiple crossovers where single particle gaps could be switching, and then you're comparing it with an overall rho s. Yeah.
Yeah, actually a related question. So in one of your first transparencies, you showed that the gap opens in the finite when you have a Fermi circle, and then maybe could you put that up again? Actually, quite at the beginning. So
Yeah, I can go and look.
Okay.
I'm almost there.
Yeah.
Let me. Yeah.
Well, yeah, there was a few, I think that, yeah, The previous.
This one.
Not really. Well, the previous one where it was even more simple, I think.
Okay, let's try this.
Okay, so indeed, yeah. There, the gap opens at the finite Q, right?
Mm-hmm.
And you make the difference with the system where the gap opens at Q equal 0.
Right here.
So you can imagine a system which has a very small Fermi surface. How would you distinguish that from the case of where it's exactly at Q equals 0?
Your underlying Fermi surface. Okay, let me just bring this up. So, let's see. If you look at the underlying Fermi surface, right? You have, so your up to this value of T, the system is a band insulator, right? And only after this it is becoming a metal. So even while the underlying bands, the underlying system is insulating, it has already become a superconductor. So this BEC is not being born out of something that already had a Fermi surface. Okay, but it is being born out of, so something like this would be good, that you still have a situation where your band gap, the single particle gap, has not closed. But the two particle excitations are already driving it into a BEC superconductor.
It's more experimentally, you may see a gap which opens in Q space by scattering, for example.
So that gap in Q space that opens up would be like this. Would be, if there is no Fermi surface in the underlying state, the gap that will open up will be at the Q equal to 0 point. Am I answering your
I guess you
question?
could put Carnegal's data.
Okay,
and you see that there is a, or,
Yeah, let me put Carnegal's data right here.
or the next one.
Yeah, the next one.
Yeah, so it's very hard to really tell apart. You know,
Yeah,
look
you
at
see.
the last one.
Yeah, these two. Yeah. So there you will have some.
You're approaching that.
Other questions? I have one question. How would you tell pseudo gap from this kind of local pair having pairing strength from pseudo gap that does not have pairing in it? What would be a good way to tell?
So you have, as Seamus was saying, you have to look at different order parameter structures in the gap thing. Is it a, so in this case, it is a C-dagger object in which the phase has become incoherent.
Right.
So here we know exactly what the pseudo gap is. But if it is, it could be something else where it has a C-dagger C with some momentum. And that also, when it is coherent, we call it a long-range ordered state. And if that object's phase becomes incoherent, it would be sort of a pseudo gap created by charge density order. So you have to look at the pairings or the order parameter structure.
But in this case, if you have local pairing within your patches, and just the phase coherence is not there, wouldn't you get this kind of Josephson response that what is his name?
Yeah.
Pablo was talking about?
Yeah, and
for something.
Right. So let me just show you one plot there. That goes to that pair spectroscopy, which very nicely brings it out. So something like this. Here we have a pairing C-dagger C. Sorry, it's a CC object, a pair object at time equal to 0. We create a pair and we destroy it at some later time and we get that spectroscopy. So if it's coherent, you can put a pair at 0 frequency because your underlying state has no phase fluctuations. But if there are phase fluctuations, then it costs some energy to add the pair. Another way you can convert this energy into a time scale. Here the time is becoming infinitely long, And so in other words, this thing here, the inverse of this is a time scale for coherence. So here it is infinitely long, and here there's a time scale which is diverging at the transition.
So my question is, in Carlo's talk and also Dimash's, when you look at magnetic field dependence, there are these Fraunhofer pattern, I think that's what it was called, that you can see as kind of patterns that show up, which is the evidence of there being puddles that are coupled through Josephson coupling. Would this pseudo-gap state also show that if one were to realize this and do the same measurement?
So that requires phase coherence, right? So if you're in this region,
You're saying you're within your patch, you do not have phase coherence?
within the patch you do.
Right.
But if you don't, the Fraunhofer pattern was ultimately averaged over the whole system. So you're not just doing a Fraunhofer pattern within the patch. The patch is...
Right. So you need like multiple patches.
Yeah, you need multiple patches and long-range phase coherence, which exists only here. Here you don't have long-range phase coherence.
And then other?
And then I'll say that in the previous transparency that you showed. So, I mean, there, so if you try to tunnel with superconducting tip, you will see a Josephson effect on the bottom situation, right? And the other ones?
So what you would see is, if, let me just do this picture here. So you would see if this is V and that is I, you would see some I, you would see some critical, right?
Yeah.
This would be in the superconducting side. And then just at the transition, this would become linear. This is at the transition. And then beyond that, it would become more like this, IV. So you would go through, this would be a very nice experiment to go through the transition and see the switching from sort of like a phase qubit to a charge qubit kind of transition.
Are there any more questions? If not, let's thank Nandini again.